This is lesson 4.4, and what we're going to get into is the intersection of two planes. So I'm going to leave the intersection of two planes to the next video, which is 4.4 part 2. This part 1 video is going to be on showing you a technique to solve systems, and that might help you in the next video. Because if you think about it, solving systems is finding the point of intersection. Get it? Intersection of two planes, right? So we normally would use substitution or elimination to find the intersection of something. But I'm actually going to show you a new technique, which is using matrices. Matrices actually isn't part of the curriculum, and so if you want to use this or you want to use substitution elimination, it's really up to you. Okay, so I'm going to show you matrices, then you have the choice as to which one you want to use. Okay, so matrices is actually the plural of matrix. So matrix is the singular. We have one right here. And a matrix is a rectangular array of numbers that's arranged in rows and columns. And so they usually are surrounded by these square brackets. And if you want to name it, we usually use a capital letter. So I can describe this matrix with the number of rows it has, and so this one has 2, and how many columns it has, so this one has 3 columns. That means that I would call this matrix a 2 by 3 matrix. Okay, now getting into linear systems, I can use matrices to help me solve a linear system. So in grade 10, you were given something like this, and you were told to solve it, and that generally meant give me the point of intersection. Give me a point that lies on both of the lines. So you guys would do substitution elimination, or if you have enough time on your hands, you would graph it, which is a lot of work. Okay, but we can actually do something that's a little bit shorter, as in it's less writing, which is the matrices. Okay, so how do you actually put them into the matrix? So first you put square brackets. Okay, and I have equation number 1, which is my line 1. Whatever the coefficients are in front of your letters, you're then going to write into a row in your matrix. Okay, so this is equation number 2, and so we have a 3 and a negative 1. And so 3 and negative 1 go here. All right, and that means that number 1 will go here, and number 2's numbers will go here. This is a matrix of just the coefficients. Now, if you wanted to add in the constants as well, you can see it on the right-hand side. It's called an augmented matrix. Basically, what we do is we take the equal signs, and we don't write an equal sign. We actually just write a line. So that line is going to represent the equal signs. Anything to the left of that line is basically your coefficients for your x and your y. Anything to the right is going to be your constants. And so this is what a matrix looks like, and what you don't have to write anymore is the x, the y, the equal sign, but just know that they're there. Okay, so this is still like the orange line and the purple line, but all we're writing are just the numbers. Okay, so now that we know how to put the numbers into the matrix, what can we do with them? Well, we can do any operations like add, subtract, multiply, and divide. You can even swap the rows around. So if you want to take like the purple and the orange and you want to change like the orange to the top and then the purple to the bottom, you can do that. You can multiply them by a certain number, like a scalar. You can add and subtract them from each other. Okay, so what I'm going to show you is what we normally would have done in grade 10. We probably would have done substitution, elimination. I'm partial to elimination. And so if I had equation number 1 and equation number 2 from above, I would be like, oh, okay, those y's look like they can disappear really easily if I just add the 2 lines together. Okay, so if I add them together, I'm going to get 0 y's. I'm going to get 5 x's, and on the other side of the equal sign, I'm going to get a 9. Then I would divide both sides by 5 in order to isolate x, and then I have my x, which is 9 over 5. I could then take that answer, substitute it into either equation, and get my y. Okay, so now let's see how to do a matrix. So using the matrices, what I would do is I would put all of the numbers into the matrix. And so remember, this is like my equal sign, right? And I have my constants on the right-hand side and all of my coefficients on the left. So then what I would do is I would start to anybody that's reading your work will probably want to know what exactly are you doing? And so make sure that you write the steps down. Explain to the person who's reading this how you got from one matrix to the next, okay? Because it can be super confusing. And so this one is saying, well, I took row 2 and I'm going to add it to row 1. So here is a very important note. Whichever row you decided to write first is the row that's changing. And so notice that the purple does not change later on because you wrote it second. Okay, so we're only going to be changing and affecting the second row because you wrote it first. All right, so if we add them together, we're going to go, I'm going to take the 3 from second row and I'm going to add it to the 2 from the first row because remember, these are your x values. And so essentially you're adding your x values together. And I'm going to get a 5. Okay, let's try that again. I'm going to take my second row, -1. I'm going to add it to my first row, 1. I'm going to get a 0. Okay, the 7 is going to add to the 2. I'm going to put my answer down here, and I have not changed row 1. Okay, so now the next step. Actually, you know what? Maybe I should explain this step. This one is our 5x plus 0y equals to 9, right? Isn't that just this? So essentially what we've done by adding the 2 rows together is I've done this. Do you see how matrices are actually very similar to substitution elimination? It's just you're not writing all of the x's and y's and all the steps. Okay, now let's see the next part. I'm starting with R2, which means it's the line that's changing. So notice that line 1 does not change. Okay, and I'm just going to divide everything by 5. So I'm going to divide this guy by 5. I'm going to get a 1. Divide this guy by 5. Get a 0. Divide this guy by 5. And I'm going to get a 9/5. And isn't that what we did over here? Divide both sides by 5, get 9/5 as our answer. Right? Because x plus 0y's, which essentially means that I've solved for my x, and it's going to equal 9/5. Okay, so again, very similar to substitution elimination. And you're going to be like, okay, you've taught me how to put numbers into the matrix. You've now taught me the steps. Where's the intuition? How do I know what to do? All right, let's get into that. Your goal is to take any matrix that the teacher throws at you, or I guess any system of equations, and then you're going to put it into row-reduced echelon form. That's a lot of words, but the words sound kind of cool. Okay, so echelon basically means, and I think this is correct, that it's a staircase or like stairs in French. And so what you're trying to do is create almost a staircase where you have a diagonal set of ones. Okay, so this is going to be my staircase right here, a diagonal set of ones. Anything above or below the ones should be zeros. And so you're trying to aim for all zeros here and here. The reason why you're doing that, and let me just erase all that so that you can see, is because if everything is ones and zeros, you've essentially solved for what you're trying to find. Because remember, this is my x, so you have a 1x plus 0 y's, which means you don't even have a y, is equal to 8. And so you'll solve for x. The bottom is 0 x's plus 1 y is equal to -3, and so you solve for y. So when you have your x, your y, and your z all as ones, you have 1x, 1y, 1z, which means that you have all of the numbers that it equals to. As in you've substituted and solved and you've come to the final answer. Okay, so let's take a look first of all at these 4 examples right underneath, which ones are actually in row reduced echelon form. So these guys have that staircase diagonal of 1s, which is perfect. By the way, your staircase could be longer. It doesn't really matter as long as these guys, your numbers, which we call the pivots. Okay, so these guys are like your pivots on your staircase, right? They're all 1s. Okay, so even this guy is fine. Okay, the only problem is we have all 0s at the bottom. And it's actually not a problem. You can have all 0s at the bottom. It just means that here's your x, here's your y, and here's your z. So in this case, 1y is equal to 3. Okay, so that I got, right? This is telling me that I have no idea what my x is, and I don't know what my my z is. But I know that 0 x's is equal to 5, and also 0 z's is equal to 5. And so there's really no such number that works for, and so this system probably doesn't work. Okay, or it might tell you something about something being parallel. Now let's take a look at the one that I've X'd off. This one just isn't done yet, and so you do have that staircase, but there's that 5 that's still there, and I'd really prefer it to be all 0s if possible, because this is telling me x plus 0 y's plus 5 z's is equal to 3. That didn't really solve for anything. Do you see what I'm saying? Like, it's still not simplified yet, and that means that we probably still have some extra work to do. Okay, so let's take a look at some examples. I've already pre-done them just to make it a little bit faster, and so try to follow along. I'll try my best to go a little bit slower. Okay, so example number 1, solve the system, as in give me the point of intersection. Using matrices. Okay, so we're going to try our best to use matrices. And by the way, the Gauss-Jordan elimination, see, now this is my first time teaching this stuff, and so I'm not super familiar with the names. I believe Gauss-Jordan is the person or people, probably people, who created all this or who discovered the row reduced echelon form. Okay, but don't quote me on it. Okay, first things first, we're going to put everything into a matrix. So here's my equation number 1. I'm going to put all of the coefficients into equation number 1. Okay, then I'm going to do equation number 2. Now, it doesn't have an x or a y, and so I'm just going to put 0s in for my x and y. It does have one z, though. Okay, lastly, I'm going to do my third equation, which is no x's, 1 y, 3 z's. Okay, so I'm going to put a 0 as a placeholder for my x, 1 for my y, and then 3 for my z. And I put the line that makes all the equal signs visible. Okay, so this line right here. And then I also put all of my constants on the right-hand side. So remember, the goal is to try to get that diagonal set of 1s and everything else to become a 0. And you can add and subtract and swap different rows if you want to. Okay, so first things first, I showed my steps. And so basically what I did was I took row 2, which is the orange, and I changed it. Okay, so I've swapped it with row 3. Okay, so now you'll see in the next matrix that row 1 was not touched, but I did end up swapping both of the teal and the orange. And the reason why I wanted to do that is I'm getting closer to having the 1s in all of the diagonals. Okay, now I'm just going to change the middle back to orange so that you can follow. As I'm just going to change the colors, guys, so that you guys can follow the answers. There we go. Okay, let's take a look at the next step. So row 2, which is the one that's going to be changing, is going to subtract 3 times the row 3. Okay, so let's try that one more time. What you're going to do is you're going to triple row 3. So if I triple row 3, this will be a 0. That'll be a 0. That'll be a 3. This will be a -6. Then what I'm going to do is take the second row and minus them. So 0 minus 0 is going to be 0. 1 minus 0 is going to be 1. 3 minus 3 gives me a 0. Negative 3 minus 6 is going to be a positive 3. Notice that I have not changed the other two rows. And so again, whatever I mentioned first in my step is the row that's actually changing. Okay, that's great because I was able to get a 0 right here. And so I'm getting more zeros in. All of my diagonal ones are in place. Now my last steps is I got to figure out how to get rid of these guys and make them into zeros as well. Okay, so the next one, what I did was, let's get rid of some of these so that I can see a little bit better. Okay, row number 1, which is the one that's affected, that's the one that's going to be changing. Notice that the orange and the teal don't change. Okay, so I'm going to take row number 1 and minus row number 2. Okay, so row number 1 is going to minus row number 2. I'm going to get a 1. Minus, I'm going to get a 0. This one subtract this one, I'm going to get a negative 1. And this one subtract this one is going to be a 3. Okay, that's perfect. Now I have another 0 out there. I'm almost done. And so my intuition is saying, well, I want this one to be a 0. Maybe if I add it to this guy, I will get a 0. And you got to make sure that any of the steps that you're taking, you don't accidentally mess up the rest of your matrix. So you still want that diagonal of 1, 1, 1, and you also want zeros everywhere else. Okay, so what I'm going to do is I want, obviously, the row 1 to change because I want this to be a 0. And so I'm just going to add it to row 3. And that means if I take all of the row 1 and add it to row 3, I get my nice 0 right there. And now I have x by itself, y by itself, and z by itself. That means that I have the point of intersection, which is an x value of 1, y value of 3, z value of negative 2. And I can put that into an ordered triple. Okay, so I'm going to show you a couple more, but they're essentially the same thing. Solve using Gauss-Jordan elimination, basically the same thing, okay, to convert to row-reduced echelon form. All right, so put everything into your matrix first. This is going to be my purple. I got 2 and a negative 1 right here. I also, oh, it looks like they have z, so I don't have any z's. I'm going to put a 0 as a z, and this is my constant. So that's going to be my equation number 1. Equation number 2 in orange, I might want to move that z over to the same side first because I want my constant to be visible. Okay, so I got a 1, a negative 2, and then also a negative 1 for my z. All right, and then the third one, which is no x's, and then I got 3 for my y and 2 for my z, negative. Okay, now that I have my initial matrix, I'm going to start to try and get that diagonal set of 1s, everything else as 0s. And it takes a little bit of practice. I mean, this obviously, even substitution elimination, took a little bit of practice before you started to gain that intuition. And so just work with it a little bit. After a while, they kind of are just like little puzzles. Okay, so here are my steps. I'm going to change up row 2. Nothing else changes, so this stays the same, this stays the same. Okay, so double row 2. Let's double all of these. Negative 4, negative 2, double that is still 0. And then I'm going to take all of my green numbers and subtract row 1, my purple numbers. So 2 minus 2 is going to give me a 0. Negative 4 minus negative 1 is going to give me negative 3. Negative 2 minus 0 is still a negative 2. And 0 minus 5 is going to give me negative 5. So this is nice. Now I have a 0 right here. Perfect. Okay. Going on to my next step, what I'm going to do is I'm going to change up row 3, but I'm going to leave the other 2 rows the same. Okay, and I'm going to add row 3 plus each of the ones on the top for row 2. And so notice that row 3 has changed, and now I get an additional 0 at the bottom right here. Okay, I'm going to continue working, and so I'm going to take row number 3, I'm going to triple it, sorry, row number 1, I'm going to triple it, so that's 6, -3, 0, 15. And then I'm going to subtract row 2. So I'm going to subtract each of these guys. And that'll give me my 0 right here. Okay. Continuing on, like it looks like I'm getting a lot of zeros, I might want to try to aim for this one to be a 0. So let's see. If I add double row 1, so I'm going to double these, that's still 0. That's a 4. That's a 40. If I take that and I add it to the bottom row, so add each one to the bottom row, I will then get a 0 here. So that's a lot of zeros already, and I'm thinking my next one is I want to get this one into a 0, and so if you follow the rest of my steps, I can then get this one into a 0, and actually the very last thing, which is probably the easiest, is if you leave that diagonal to all these random numbers, you can then say, I'm just going to divide the entire row 1 by 12, the entire row 2 by -6, and the entire row 3 by -4, and so imagine like you just have 12x and it equals to 39. Obviously, you're going to divide it by 12 to get x by itself. This is basically saying you have -6y is equal to -9 over 6. Sorry, not 9 over 6. Just -9. And so you want to divide by -6 in order to get just the y by itself. And this would be -4z, and so if you divide both sides by -4, you'll get z by itself. Okay, so you are left with all of these guys, which are your answers for your x, y, and z, and we would put them either into, I mean, you can write them like this, or you can write them into a point. It's up to you. Okay, so I'm going to leave this one for you to just look at. I noticed that I could end, and this one looks a little bit different at the end. We are in row reduced echelon form. It's okay if anything after the ones, so anything to the right of the ones, can be numbers, as long as you do have that 0 above and below the ones. Like I said, this actually isn't finished, because if you think about it, this would be 1x minus 3z is equal to 10, and this would be y plus 2z is equal to -7. So this isn't actually finished yet because we don't know what z is, we don't know what x is or y. So when we get that far, we're going to do something extra. And this is how I'm going to finish off this lesson. We're left with something like this. And that's kind of an issue because we want like an actual number for x, y, and z. But it doesn't always happen. And so our intersections are not always just a point. Sometimes, especially when you're talking about two planes intersecting, I don't know how to draw this. If you intersect, okay? If you think about two planes intersecting, they could intersect not at a point, but at a line. Okay, so sometimes you'll get an answer that's not actually an x, y, z coordinate. You'll get something like what we have up here. And so when we have something up here, z could be anything. And if z is anything, well, whatever z is will affect my x. And whatever z is will obviously affect my y. And so why don't we just say that z can be some scalar amount? When we say something like that, we're going to substitute k instead of z. So we're going to put k in here instead. And we're going to put k in here instead. And we're just going to solve for our x and y. And that means that we have x is equal to 3k plus 10, which I can then put into a coordinate form if I want to. Y is equal to 2k negative minus 7, which again I can put into a coordinate form. And then z we're just going to say is k, which we're going to put right here. And so depending on what k is, my point is going to change each time. And so if you decide to sub 1 in for k, you're going to get a certain coordinate. If you sub 2 in for k, you're going to get another coordinate. And so as you can see, there are infinite number of points that can be available, which means that you have something that looks more like a line. Okay, so the line, what we can do is we can just rewrite this into vector form with a k parameter. And so this 3 in front of the k, this -2 in front of the k, and this 1 in front of the k goes right here as our direction vector. The lone 10, the lone -7, and the lone 0 are going to be my point. Okay, so you can use matrices in order to solve systems, and this will help you out in our next video when we have like these huge planes that we have to intersect together. Okay, so your choice, whichever one you like better, substitution, elimination, or you can use matrices.